I got thoroughly sidetracked talking about computer stuff. Shockingly, someone who teaches in this program is interested in computers. Who knew? Um, so anyway, I don't have any announcements about anything that's going on. We don't have anything going on other than surprise. There's a quiz. I know. Don't get too excited. Um, but it's going to be on graph theory. Also, big surprise. So yeah, no announcements. So I guess we'll just get going so I can hand you the quiz, which I screwed up. Not in a sense of like it's like really impossibly hard or something like that. It's that I asked you to do something, and then like half the students in my last class were like, Travis, but I found the minimal coloring set, and then I was like, shit, because I wanted you to do it in 4, and you're doing it in 3. Stop being good at it. So I'll talk about that when I hand it out. But anyway, last class we talked about graphs. We introduced the concept of them. They are basically defined by 2 sets, a set of vertices and a set of edges, and we can visualize them. They're just a nice discrete object, right? They sort of abstract any problem you have that involves nodes and connections between them. So like just in computing, those are all over the place, right? Just think of like a network, right? A network diagram is a graph. Where it's probably a weighted graph where you have, response time is your edge weights. So like they're all over the place. And then we started talking about the different types of graphs. So like connected graphs, simple graphs, directed graphs, weighted graphs. There's just all kinds. And I could keep going on for hours about that. So there's just lots. And then once we started talking about the various types of graphs that we have, we started exploring algorithms that we can perform on these graphs. So one of them was graph coloring, and on its own, the algorithm for coloring a graph it's called the greedy algorithm. There are a lot more advanced algorithms that produce better results, but the algorithm on its own is kind of mundane. So you might be like, okay, well, what does graph coloring have to do with computing? Why does it matter? Well, there are lots of situations where we would care about a minimal coloring, where colors might not necessarily be colors, they might be groups or something like that. And a natural question is, I have this graph, my network graph, how many ways are there to color it? Or I have this graph, what's the smallest number of colors I need to color it? Both of those are NP-hard problems. What that means is they are non-polynomial problems in computing that have no predicted polynomial time solution. So what that means is they're just really, really inefficient, and that's just by design. We cannot make them efficient. We can't. It's impossible. So the fact that there are some algorithms and problems that are like that is actually very important to security and cryptography. If P equals NP is true, we're screwed. Security is broken now. So it's probably not true, but we haven't proven it yet. So the point is there are interesting problems related to graph coloring that aren't necessarily how do I color this graph, specifically it's how many colorings are there? How do I get the smallest number of colors? That sort of thing is an interesting problem, and it's a hard problem to solve. Similarly, the traveling salesman problem is a hard problem to solve. There's just lots of graph theory problems that are computationally interesting and hard to solve. And then we started talking about trees. So the whole reason I was talking about graph theory ultimately is to present some interesting algorithms, but to talk about these. These are a data structure in computing that are everywhere, right? So we have this interesting thing, this dichotomy of there's computer scientists and there's computer programmer. So a computer scientist is the one who is like digging into the theory and developing algorithms and that sort of stuff. And the computer programmer is the person who actually builds those algorithms, right? I would say, I'm a computer scientist. Here's how you do it. And then you'd be like, okay, I'm going to go do it. And then report back on the problems that you run into with it. So there's that sort of relationship there. Trees are interesting because there are lots of theoretical things about them, but they're also very practical. They're everywhere. They're a good data structure to be using a lot of the time. So while you might not run into graph coloring problems, you will definitely run into trees. You might even, in this program even, be looking about how to solve a problem, and you'll end up on Stack Exchange, and someone will be like, oh yeah, I implemented that as a tree, and I used depth first search, and it solved the problem. And you'd be like, great, I'm glad Travis talked about that, and I forgot about it. So trees are everywhere. So we're just going to essentially talk about them a bit more. I gotta organize my notes better. So remember, trees sort of had this structure. So something like this, where we sort of have this root node up here, right, the top of it. I, for some reason, have an R in my picture, so I'm just matching it. Don't laugh at me. So something like this, right? So we've got this sort of root structure here, and then we have these sort of endpoints that have leaves. We call them, they're leaves. And we have the idea of a parent-child relationship in graphs, and it's a natural one, right? So this right here has A as a parent and has D, R, E, and F as children, right? So it's a natural concept, right? I could write it on the board, but it's just one that's intuitive, right? So we're not going to dig too much into the nitty gritty of the definition. But I am going to say there is an important type of tree. And that's a binary tree. So this is not one of them. So whenever you see binary in computing, it means 0 and 1, two choices, right? So a binary tree has at most 2 children. So this is not a binary tree because this node here has 4 children, right? So it's not a binary tree. So I'll say vertices. I can't spell today. Vertices have at most 2 children. So we can then refer to left child and right child, right? Because there's at most 2, so we might as well distinguish, right? We're gonna, when we're drawing it, we got 1 on the left and we got 1 on the right. So again, this is not a binary tree, but I can just sketch one out real quick. Something like that, right? So this has 2 children, this has 2 children, this only has 1, and that only has 1, but that's okay, right? Just as a sort of rough sketch of what a binary tree looks like. So naturally, dealing with computers, binary is important. So the concept of a tree that also sort of encapsulates this is also an important type of tree. So when it comes to trees, there are all kinds of algorithms that we are interested in. So I'm going to present a couple of them. The first one I'm going to talk about is tree search algorithms. So these are ways to tree searching or traversal, we'll say. So there are ways to sort of just go through our tree in a sort of systematic way or to search through it, right? Like we've got this tree here and I say, is G in the tree? Well, how do we efficiently do that, right? How do we efficiently and algorithmically go through this instead of just, as people, if I said, is G in the tree, you'd be like, it's right there, right? But your computer can't do that, right? It's not going to look at this picture and just be like, it's right there, right? It needs some way to sort of algorithmically go through this. So there's 2 ways that we're going to talk about to traverse a tree or to search a tree. And that's the idea of breadth first and depth first. So breadth first, what that's saying is we're going to sort of we're going to cast a wide net first, right? So a tree has this sort of depth, right? It goes down, but it also goes wide, right? So this is saying we're going to go wide first, and then if we have to go deeper, we'll go deeper. That's what this algorithm is going to do. So how do we do this? First, pick a vertex, call it V.
So this, I'm saying this is for trees, but it really also works for graphs. I almost wrote Garfield. So these search algorithms also work for graphs. There's nothing special about them being trees here. So we're going to pick a vertex, and we're going to call it V. That's our sort of starting vertex. This is just for reference. If we're dealing with a tree, though, we kind of have a natural one. If we're told just pick one, we should be picking the root, right? So in a tree, pick the root, because it's sort of it's the originator of everything in our tree, so we should start there, right? That seems like the natural starting spot. Okay, so we're going to pick some vertex, and we're going to mark it visited. So we're saying, hey, we've been there, right? We've already checked this node. So if we're doing a search algorithm, we're going to also want to do a comparison, right? We're going to say, at this node, is this what I'm looking for? If searching, check this node. So either it's what we're looking for or it's not. If it is, we stop. If it's not, keep going. If we're just doing a traversal, then we're not going to search, right? We're just going to do everything. We're just going to go through this algorithm. Okay, so next, what we do is we're going to visit every connected node to the one we're looking at. Visit all connected nodes. Vertices. And mark them visited. And then once we've done that, we say, okay, for all of those nodes that we just visited, do the same thing. Find all the ones connected to the ones we just looked at and keep going. So then visit the connected nodes to the connected nodes and so on. So we kind of write it like this. It's a bit hard to decipher. So an example on this exact tree is probably the best way to see it. So what we're going to do in this, let's go through this algorithm, is we look at it and it says pick a vertex. So we're looking at a tree right here. So let's pick the root. And so we're going to say this is A, right? We're writing it down. So either, let's say we were searching for something, we would just do a comparison. We would say, is it A or not? If it is, stop. If not, keep going. Now it says, visit all connected vertices and mark them visited. So we're at A. We're going to look at all the things that are connected to A and mark them visited. So that means essentially we write them down or perform whatever check we want on those vertices. Now we've marked those visited. Visit the connected nodes to the connected nodes. So these are the connected nodes. What's connected to those? So in this case, D, R, E, and F are connected to B. D, R, E, and F. And G is connected to C. Next, what's connected to all of those? Just H. And then we're done. So if we were searching for, say, let's say we were searching for E. So the way we would have gone through this is we would have went and checked all of these and got to E, and we would say, there's E, right? This is the steps we would take to search for this. But the interesting thing about this is it sort of creates a tiered structure, right? So we've sort of got these tiers, these chunks, and those are all the things that we're visiting at once, right? So we visited A, and then we visited B and C, and then we visited D, R, E, F, G, and then last we visited H. And so we've sort of got these distinct chunks that we're going through here. And so that's essentially what breadth first does. Breadth means, spread your wings as far as possible, spread your net as far as possible. So think examples of where this algorithm is useful is solving a maze. Right? You've got some maze like this. So like, let's say this is our maze, right? We've represented it as nodes like this. And as people, we can very clearly find the shortest path through this maze, right? We would just go boom like that. But let's see what our algorithm does on this maze. So it starts at a root and then visits the connected nodes and then visits the connected nodes and then visits, and then if this were our exit, we've just found it, right? So we would stop at this point if we were trying to find the exit to a maze or the shortest path. So this algorithm is very useful for finding these shortest paths. Another way, actually, this is courtesy of a student from the previous section. He said this. Think of like the water in a river, right? If you've got a river that branches out like this and you start it from the source, it's going to pour out like that, right? And then it will reach the little individual streams and stuff, and it will split out from there. That's what this algorithm does. So this one is sort of an iterative algorithm, right? It starts at the root, and then it says, okay, and then visit all the things beneath me, and then visit all the things beneath that, and then all the things beneath that, and so on. So the other one, depth first, is in some sense the opposite, but also maybe not really the opposite. This is what we would call an iterative algorithm. This is sort of going to be a recursive algorithm. It's going to start out the same. We're going to pick a vertex to start with. And of course, if we were dealing with a tree, just pick the root, right? Start with that. And we mark it as visited. So what do we do next? Well, we just pick any vertex that's connected. So pick any connected vertex. Let's call it Y, because now we're picking a specific one, and mark it as visited. Okay, next, do the same thing, right? Pick a vertex connected to Y. Connected to Y. And repeat, right? Just keep going. So when do we stop? Well, eventually we're going to get to a point where we have no connections that we can go to, right? Eventually, we reach a vertex with no unvisited connections. So once we get there, we just backtrack until we find one that we haven't visited. When this happens, backtrack until we find a vertex
with unvisited connections. And obviously, visit those. And so if you sort of travel in this way, you'll eventually run out of places to visit. So what does this one look like? Well, so I could have recycled the tree I have written down, but again, if I'm going to make you write it, I also have to write it. I'm so kind, right? Okay, so I'm going to use the same tree as before. So A, B, C, D, R, E, F, G, H. When I was building this tree, I just was like, I'm going to add an extra node. And I was like, what letter? And I was like, I'm too lazy to figure out which letters I use. So I'm just going to use R. That's how that happened. Okay, so anyway, let's take a look at this tree. And we're going to do this algorithm on it. So it says, pick a vertex, any single one. We're a tree, so it's natural to start here. Now, the reason why I'm saying we start here naturally is you might say it's arbitrary because in this graph, yeah, you could technically start anywhere. And that's true. But if you're implementing this as a data structure, it's pretty natural to start at the root when you're sort of traversing these. When you're actually implementing this algorithm in your computer on something that looks like this, the root is the most easily accessible thing. So starting there is natural. If you tried to start here, then you're going to have to actually, you're trying to solve the problem by doing your problem. If this is what it looks like and you want to start here, you have to figure out how to go from here to then start there. So it's like you haven't really solved, yeah. Anyway, we're starting at A. So we're going to write down A. Now what this is saying is pick any connected vertex. It doesn't actually matter, but in terms of algorithms, you're going to pick something and sort of be consistent about it. So we're going to pick going left where possible, right? Left to right. So we're going to go to B. And we mark it as visited. Now what this says is once you've done that, pick another one that's connected to it, right? So this says pick our root, mark it as visited, pick any connected. We just did that. We picked B and we marked it as visited. Now pick another vertex connected to B and repeat what we just did, right? So now we're going to pick D and mark it as visited. And then we're going to pick H and mark it as visited. And now this is where the algorithm is quote unquote different. We say, okay, we just got somewhere that has no unvisited connections, right? We look at H. Well, it's only connected to one thing, and we've already been there, right? So now, at this point, we have to backtrack, right? So we're going to go up, and we're going to say, okay, now I'm at D. Does D have any unvisited connections? No, it's only connected to H and B, and we've been to both of those. So we backtrack again. Now we're at B, and we say, okay, do I have any unvisited connections to B? Yes, I can go to R now, right? I haven't been there yet. So we're going to go to this unvisited vertex, and we're going to say, aha, now I have been to R. Well, I'm in the same position again. I have no unvisited vertices, right? So I backtrack back up. I'm at B again. Now I can go to E. Mark it as visited. And now we got to go back uphill. And we can go to F. And then we go back up. And now we're at B and we say, okay, is there anywhere I haven't visited? No, I'm out of places, right? I'm at B, I've been to D, R, E, and F, and A, right? So I have to backtrack now. Now I'm at A, and I say, do I have somewhere I haven't been? Yes, I haven't been to C. And now I haven't been to G. And at this point, I've been everywhere, right? So this is a bit more spidery. Like it's got a lot more back and forth. But this one I don't know if I would say it's easier to implement, but it's kind of nice that it's a recursive algorithm, because what's it really doing here? It says, okay, started a node, visit one of these, right? I'm at A, I'm going to call visit tree, visit everything in B. And then I'm going to call visit everything in D. And then I'm going to call visit everything in H. And it's going to sort of recursively do that. So in your Python course, did you talk about stacks and queues at all? Yeah? Okay, program logic. Okay, so the difference between these algorithms, they are almost actually identical. The difference is when visiting nodes, in breadth first, we put stuff into a queue. In depth first, we put it into a stack. So that's also why depth first lends itself naturally to being implemented recursively, because function calls are also a stack, right? When you call a function recursively, you are putting a call of it onto the stack, the memory stack, and you can sort of unpack that. That also means, though, so when we're talking about recursive algorithms, I said if you've got something recursive, you can always implement it iteratively, right? You can undo the recursion. The opposite is not true. If you've got, well, let me rephrase that. Technically you can, but it's not a good idea. So this depth first can be done recursively naturally. It also means you can do it iteratively. Breadth first, you do it as an iterative algorithm. So you'd say, well, can I do it recursively? I would say yes with a Y, because technically you can, but the problem is you are now asking yourself, how do I turn a queue into a stack? Like, yeah, you can do that, but like it's not great. And it's going to add a lot of overhead to an algorithm that already has very minimal overhead because you're doing it iteratively. So you're just adding extra stuff for no reason. So, you know, these algorithms are interchangeable, but not easily interchangeable. And we can kind of see here that they produce different output too, right? Like completely different. So this was what we call DFS, depth first search. What did BFS, breadth first search, give? Well, it went A, B, C, D, R, E, F, H. Or sorry, no, I switched it in my head. F, G, H. Right, so we see there's some similarity here, right? We visit A and then we visit B, and now things get really mixed up. They're completely different, right? So if we were asking for H, right? We said, let's say we were searching for H. This algorithm finds it pretty fast. This one is the last thing we find, right? So in some sense, one of them is better than the other depending on your circumstance, and that's really the struggle with choosing algorithms in programming is, how do you know? Sometimes you don't. Sometimes you're like, well, I know that there's a worst case scenario I can run into. So either I'm going to have to just accept that as my reality, that sometimes that's going to happen, and maybe I'll pre-check my data to see if I'm in those worst cases, like as an example of a tree. So if you had something that looked like this, right, and you wanted this one right here, then depth first is going to be terrible, right? It's going to be really inefficient because it's going to go all the way down here to the deepest node and say, it's not there, and then it's going to go here. Breadth first would, boom, you're done, right? So if you implemented depth first, though, that's what you chose to do, you might say like, well, maybe I can check my data beforehand really quickly and see if I'm in some of these bad cases, right? And if I am, maybe I would call breadth first instead. Maybe I would clean up my data somehow to make it not this case, whatever, right? Like there's lots of little optimizations you can do. But sometimes when programming, you are faced with the reality of worst case scenarios, right? And it's kind of important to make sure that your algorithm still isn't awful in the worst case scenario, that it still behaves okay. Okay, so I mentioned it, that I called this section tree traversals, but then I put in parentheses, hey, this also works for graphs. That's technically true. So let's actually try it on a graph instead of on a tree to see that it works. But it's sort of natural to visualize in a graph, in a tree, because you sort of have this sort of spreading out structure. In a graph, it's a bit weirder looking, right? You don't have sort of a natural start point. So I'm going to I have to try very carefully to draw the same picture here because it's a bit hard. Okay, so this is A, B, D, C, E, F, G, H. Okay. So this goes around like that. Okay. So this is our graph. So in my notes, I start at A, but this is a graph now. So I just started at A because, well, the node is A. It's the alphabet. But it's arbitrary. So where should I start? I'm going to do both of these algorithms on it. Where should I start? Okay, sure. Let's start at A. So let's do breadth first search. So I'm calling it BFS, breadth first search. So we started at A. So we mark A down, and now we say we visit everything that's connected to A. And mark it as visited. So that's B, D, and C. And now, from there, I visit the neighbors of these ones. So from B, I would go to H and E. From D, I can't visit anything that hasn't already been done, so I would just skip it. From C, I can go to F. Right, so we're sort of just casting a wide net. We hit everything I'm next to, and then from there, I hit everything those are next to. Then I go to H, and I say, well, what's next? G. And now I've hit everything, right? So just like with the tree, we do sort of have this sort of tiered-like structure, right? Then we went to B, D, C, and then we went to H, E, F, and then we finished at G, right? So we've sort of got these distinct chunks that we're visiting in order. All right, but let's do the other one. I have these colors switched. Oh, sorry. So we're going to do depth first search now. We're starting at A. So we start here at A, and we visit A. Now, it doesn't matter which one we pick. It just says pick any one. Again, I'm going to lean to left to right. You could do right to left. Doesn't really matter. But you need to sort of have some kind of consistent idea of how to do it. If you're implementing in the computer, you're just going to do a for loop, right? Over all the nodes, and it'll come out however it comes out. So in this case, we're going to go to B. And then we visit a neighbor of B. Let's go to H. And then we visit a neighbor of H. We're going to go to G. And we visit a neighbor of that. We're going to go to F. And now we have a choice. So again, we're going to prioritize left to right here. So we're going to go to E. And then we can go to D. Now we're in a situation. I'm at D. I could go to A, but I've already been there. I could go to E. I've already been there, right? So now I have to backtrack, right? So I have to go, okay, I went to D from E. Can I go anywhere here? No, I've already been everywhere here. So, okay, from E, I go back to F. Can I go anywhere here? I can go to C. And now I've been everywhere, right? So you see, this gave us a very different path through, right? We went like this, sort of went around the outside, and then we had to backtrack to get there, right? What I would say, efficiency of these depends very much on where you start in a graph, right? Because if I started somewhere else, maybe I didn't have to backtrack at all, right? So that alone is an interesting problem to try and solve. Okay, so these are the sort of what I would call important search algorithms for graphs. For trees specifically,
And binary trees, there are even more. Specifically, if you have a binary tree, there's something called pre-order, post-order, and in-order. This is just an aside, so you don't have to worry about writing this down. So let's say we had this tree here. So when we're actually implementing this in a computer and we're writing down our output, we sort of say, okay, when we're doing this depth first search, we're doing it sort of recursively. Do we go down the left side first, then do the middle, and then do the right? Do we do the middle first, then go down the left, then go down the right? Do we go down the right and then the middle and then the left, right? Like it's sort of arbitrary. So there's a bunch of different ways you can do it. I would say the most common is pre-order, in which case you go left, middle, right, or sorry, that would be middle, left, right, or in order, which would be left, middle, right. It's just there's lots of different ways you can do it. So that's just a bit of an aside. But speaking of binary trees, there is one more concept I want to talk about related to them. And this is, I would say it's a bit of theory more than anything, but I think they're really neat. The Marge Simpson meme, I just think it's neat. That's me in this whole section, I guess. So it's the concept of a binary search tree. So this is a binary tree with an extra condition. And it ends up being a math condition. Because, I mean, you look at this graph theory, and it's one of those things where you're like, this doesn't really seem like math, right? With math, we're used to like formulas and variables and numbers and whatnot. And this stuff doesn't really feel like math. This is like way more math than that stuff is, to be honest. Math is very theoretical, very abstract. That's kind of the important thing. But we're going to bring it back to, just numbers here. So what this says, well, I guess we could say it's two extra conditions. Vertices are numbers, generally speaking. And if you are looking at a node or vertex, everything in the left tree, so like the left children and everything on that side, is smaller than the one we're looking at. So the left subtree is smaller than this vertex. And the right subtree is larger. So what do I mean by that? So you've got something like this, right? And maybe there's more stuff down here. Right? You just keep going. But let's say this is the number 10. The left side here is smaller. Everything here is smaller than 10. So like we would have 5 here as an example. And then maybe this would be 3 and this would be 6 and so on. Everything on this left side is smaller. Everything on this right side is bigger, right? So, this would be 17. Here would be like 23, whatever. Everything there is bigger than what we're looking at. Now, this kind of lends itself to a weird looking structure because this condition here is true at every single vertex. So that means, we go to here, we go to 5, everything to the left of 5 is smaller than 5, everything to the right of 5 is smaller than 5. So that kind of means we can't even really go much further, we can't go too far down this way, right? Because eventually we're going to get close to 10, but then it can't be bigger than 10 because otherwise it would have been over here, right? So let me just write down an example of this. And I have to be careful because these are very specific. So I've got this structure. So we've got 8 up here, 3, 1, 6, 4, 7, 10, 9, 14, 13, 16. That's kind of what I mean, right? Like it's weird looking, right? Like, you know, there's small numbers here, but it's sort of like it goes down and then goes up and then goes down and then goes up and stuff like that. But it still satisfies this important property. So like if we just pick here, everything to the left of 14 is smaller, everything to the right is bigger. And the reason why this is helpful is we can easily look for numbers in here, right? Very, very efficiently. So let's say we wanted to look for 4. So we start up here and we say, all right, is 4 equal to 8? No, but 4 is less than 8. So we go down this path. And that means we do not care about this anymore. Nothing over here matters, right? All that's bigger than 8, we don't care about it. Is 3 equal to 4? No, but 4 is bigger than 3. So now we go down the right path. Is 4 equal to 6? No, but it's less than 6, so we go down the left path. Is 4 equal to 4? Yes, it is. Cool. So if we think of this is a data structure. So that means we can envision other ways of organizing this data. Like let's say we were in an array, right? And it kind of doesn't matter where 4 is in this. It only took a few steps. But if we put all these numbers into an array, we can imagine a situation where we would have to go through the whole array, right, to find 4, in which case we went through a lot of steps that were unnecessary. But this structure lends itself naturally to just searching through, right? It's very fast. But it's also fast to find things that aren't in it. So let's say we were looking for 12. Okay, 12 is bigger than 8, so we go down this way. 12 is bigger than 10, so we go down this way. 12 is less than 14, so we go down this way. Now, 12 is not 13, and there's nowhere else to go, so that means 12 is not in the tree, right? So this algorithm is really, really fast to search through a tree. Now, the reason why I think these are interesting, and for any assignments I give you on any of these trees or anything like that, like I want to have you implement these algorithms because they're actually pretty interesting and easy to implement. The problem is building a tree. That's actually the hard part, especially building this tree is notoriously complicated. Let me not say, maybe not notoriously, it's actually more involved because we have this very specific structure, right? So you just imagine you have an array of random numbers in it, right? Well, how do you guarantee everything is laid out this way, right? There's very, very specific conditions on this. So building this tree structure is actually the hard part. And this tree is very useful for sorting because once you have it, if you visit it in a very specific order, which is in order, so you would go here, 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 here. It's now in correct order, right? It would be 1, 3, 4, 6, 7, 8, 9, 10, 13, 14, 16. Right, so once it's in the structure, there's actually a very, very immediate, instant, recursive thing you can do to just read it in order, right? So this is called binary sort. You can do it in place without a tree, but if you have the tree, it's really easy to do. Because of that, I want you to maybe play around with these algorithms. If I have you do this, I will provide you with the code for the tree. Because in your first Python course, how much object-oriented programming did you talk about? Like, not very much. So building something like this requires you to understand object-oriented programming decently well. Using it, you probably have the knowledge you need from that course to use it if I provide it to you, right? Because I would just say, here's how you initialize the tree. Now you can play with these methods in the tree to do stuff to it, right? Like here's the add method, here's the delete method, here's the traverse method, here's the search method, and then I would have you build the search method, right?
So I will give you most of the structure for these because asking people who have done one course on Python to build a binary search tree is like, that's like masochism level unfairness. That would be like, everyone would be like, Travis, why do you hate us? Why I don't know. This is like, you would end up on Google and you'd be like, I have no, like, we didn't learn how to do this. And I'd be like, I'm sorry. So you can probably understand it if I give you the code. Like you would be able to look through it and you'd be like, I see what's going on here. I get what it's doing. But for me to ask you to build it from scratch is like unfair. That would be very unfair. So when it comes to these sorts of structures, I will provide you with the structure to play around with. And this is sort of the part where it's like, hey, new section, new material, never done it before. Maybe I provide you with the structure and everyone's still like, yeah, I can't. I don't know how to use it. And that's okay because I will adjust for that. If we have that happen and I give you an assignment on like, hey, implement depth first search on this tree that I have provided for you, and everyone's like, we have no idea how to do this. It is really hard. I'll be like, fair enough. I won't do that again. So that's the part where it's like, you guys are kind of my guinea pigs for that. So that means if you're doing these homework assignments, which will be for the group projects, if you're like, these are way too hard, please tell me. Like if like, do you guys have a Discord where a bunch of you are in yet? Yeah, I see some people being like, yeah, like you probably at least are organizing in other ways. That means there's probably word of mouth. So if you see everyone as being like, man, I can't do Travis's homework assignment, then please tell me, because I do not want the homework assignment to be unfairly challenging. I just want it to be interesting. So that's why I'm talking about this, so that I can give you interesting programming assignments in a math class. So if that means it's really challenging, maybe that's not what I'm going for. Anyway, so that's all I have for